Geologists the world over have always been drawn to this range, the way it suddenly leaps out of the earth. It is truly massive, and it's always attracted our curiosity. But it turns out that the greater mystery is not in these spectacular outcrops, but what lay beneath the surrounding plains. The sandstones of the Grampians Ranges are easily visible. They form by ancient rivers and shallow seas. But what was the original land before the Grampians? What did it look like and how did it form? These questions have puzzled generations of Earth scientists. A century and a half ago, the Geological Survey of Victoria set out to understand the earliest origins of Western Victoria. Geologists Norman Taylor and Ferdinand Krauser were part of the scientific quest. From their base camps, they surveyed the land on both foot and horseback. In the evenings, with meticulous care, they plotted their findings in a makeshift office. And in a few creek beds, cutting through the plains, they found unusual metamorphic rocks. And then, on isolated hills like this one, they found boulders of volcanic rocks. They knew these rocks were both older and completely unrelated to the Grampian sandstone. But in the early days of Earth science, they had no way of knowing how these volcanic rocks got here. It would take 150 years and a revolution in Earth science for geologists to finally understand what exactly happened here. This film is about the people who can now tell the story of this enigmatic part of the Earth. I'm going to meet a team of geoscientists from the Geological Survey of Victoria and Geoscience Australia. In the footsteps of the 19th century geologists, they remapped the hills and used the latest technology to peer beneath the plains of Western Victoria. They call this area the Stavely Arc. The ancient rocks of the Stavely Arc are in southeast Australia, in Victoria's west, and here, old rocks are mostly covered by a featureless plain, a blanket of much younger sediment called the Murray and Otway basins. Krauser and Taylor found their Stavely rocks in just a small area that rises above the plains. The challenge for the modern team was just how far would the Stavely rocks extend under the younger cover. Ross Cayley is one of the leading scientists on the project. He grew up in this area and for the last 30 years has been unravelling the complex geology. But a scientific challenge of this scale needed extra help.
We had to bring together a huge team with diverse skill sets. So it was geologists, obviously, to map the rocks that we see sticking out of the ground, but a lot of the rocks we're interested in, they're buried out under these plains we can see behind us. So in order to study those rocks, we had to use geophysicists to look at techniques to remotely sense those rocks.
Hidden rocks was one challenge, but another was time itself. Krauser and Taylor had reasoned that the buried rocks were from a period in the Earth's timeline that we now call the Ordovician. As Victoria's fossil evidence grew, geologists realised the Stavely rocks must belong to the Cambrian period, around 500 million years ago. The 21st century team would need to build a much better timeline, and modern geochronology would help date the age of the rocks.
And it's possible to do that because some of these rocks have got tiny mineral grains in them with radioactive elements that allow us to date the actual age of the formation of that rock, and that's a really critical part of the story.
Cameron Cairns is a geologist and manager with the Geological Survey of Victoria. He helped to coordinate these experts and others.
Well, it's very rare that an individual will have all the skills, expertise and knowledge to answer and solve some of these complex geological problems. So that's where collaboration becomes really important, to bring necessary niche skills all together to try and deliver the best scientific product.
The Geological Survey of Victoria began in the gold rush of 1852. Its brief is to provide an understanding of Victoria's geology its minerals, energy, groundwater, and the information we need for infrastructure. In the 1870s, Ferdinand Krauser and Norman Taylor were original members of the team. Their job was to explore the whereabouts of gold and mineral deposits. Like now, they knew the key to success is to firstly unravel Earth's history, because it's the Earth history that tells us about Earth processes that formed these rocks and mineral deposits in them. But this was the early days of the science, and the dynamics of the Earth were not well understood. What they did have, and their lasting contribution, was great observational skills, which resulted in beautiful maps.
Those guys did a really good job at a really broad scale, so they got all the basic elements more or less correct. So when you look at that late 19th century map, it looks much like the modern one. So it was just observation driven, and they were really good observers. We still use that data today.
But in the 1870s, the way the Earth worked was still poorly understood. Krauser and Taylor couldn't know how the volcanic and metamorphic rocks had come to be there. 90 years later, in the 1960s, the revolutionary theory of plate tectonics finally unified all the branches of geology into one logical Earth-scale system. Professor Tony Crawford was one of the first geoscientists to apply the new theory in Australia. Using geochemistry, he compared older volcanic rocks of Victoria with rocks in the modern Pacific.
Professor Keith Crook at ANU, who encouraged me with the term learn about actualism, the present is the key to the past. And he told me if I wanted to understand the rocks in Eastern Australia, I should be looking at the modern settings out to our north and east, which was excellent advice.
By the 1970s, scientists were comparing the geochemical fingerprints of old volcanic rocks with young rocks. If there was a match, they could assume the old rocks had formed in a similar tectonic setting as in the modern environment.
We had the opportunity at Melbourne University then of using some new equipment to get good compositional data about the rocks, and at the same time rocks in modern settings were experiencing the same reinterpretation. So it was really comparing old rocks with young rocks.
Tony found that Stavely's old rocks had the same chemistry as rocks in young volcanic arcs to the north and east of Australia. This meant that Stavely had started life as a line of volcanoes where two tectonic plates meet. Stavely was part of what's called a magmatic arc. Magmatic arcs are long, narrow belts of volcanic and intrusive rocks. They form as one tectonic plate sinks beneath another, in a process called subduction. Subduction induces melting, and magma rises to the Earth's surface as volcanic eruptions. To put this new understanding into perspective, I met with senior geologist David Taylor, another long-term member of the team and one of their most experienced field geologists.
So the work by Tony Crawford was crucial, and it told us there was a magmatic arc in Western Victoria. But there's two types. You can get magmatic arcs forming in an ocean or magmatic arcs forming in a continent. And that difference can be important. And the way to tell is to actually then have to go out there and map all the rocks around the arc to see where they look like they formed in an ocean or the continent. So that's the follow-up work we did on the back of Tony's great early idea.
So the Geological Survey's new generation remapped the whole area. And this evidence would help define the type of magmatic arc at Stavely. It took time and footwork, but modern mapping was a vital stage before the geophysicists and other experts could interpret their data. And modern structural geology would add a whole new dimension to the old maps.
And also there's these really tight folds. So it's apparent these rocks have had a very strong structural history. They've been subjected to a lot of deformation.
A modern structural geologist looks at the same rocks as Krauser and Taylor, but by mapping hundreds of small-scale features, they can extrapolate to the big picture.
So when Ross and I went out and started mapping, we found this big structure between two completely different rock packages. One package was ancient continental Australia on the west, and the other one was the ancient Pacific Ocean on the east. And so the boundary, the fault at the surface today marks the ancient margin of ancient Gondwana land.
Their discovery of this massive structure, called the Moisten Fault, would help place the Stavely volcanic rocks in their original setting. David and Ross had revealed the ancient continental boundary, and fossils showed it existed 500 million years ago. That's a long time ago, but just a fraction of the Earth's timeline. Significantly, the Stavely rocks seem to be related to Gondwana's boundary. But did this mean the volcanic rocks were still in their original position along Gondwana's ancient margin, or had they erupted in the ocean to be later pushed against Gondwana? Some crucial evidence to help answer this was discovered here at this isolated outcrop by George Buckland for the Geological Survey in the 1980s.
Believe it or not, Clive, this is one of the best outcrops of the Mount Stavely volcanic complex. There's a few like this, but most of the area which has the arc rocks underneath is just these sort of paddocks with hardly any outcrop at all. So outcrops like this become really, really crucial. You can see it's a breccia. If you look closely, you can see that there's individual clasts of andesite stuck all together within a matrix of volcanic detritus, all sort of cemented together now.
So what's the context of this breccia forming?
Well, this breccia is associated with other volcanic sediments, and they look like they were deposited in a subaqueous environment. So we think this is a submarine volcanic rock. But when you look in some of these clasts, this is a clast of an andesite lava. If you look quite closely, you can see it's quite vesicular. There's little bubbles and cavities all through it. So this tells us that the water it was erupted into wasn't that deep. There wasn't a huge confining pressure.
These observations suggested the volcanics had erupted in shallow waters, close to Gondwana's margin. But to be sure, the team needed additional supporting evidence. David Taylor describes one example.
There was a group in Adelaide University that had done some geochemistry, Professor John Foden out there, and he realised the geochemistry of the rocks was pointing to a specific environment where the andesites, and andesites, we say andesites, but it's really andesite, which means the rock of the Andes.
John Foden argued that Andean style or continental margin subduction had occurred in Western Victoria 500 million years ago. And significantly, the Andes are famous for world-class copper deposits.
When you look at the Andes today, they're full of the world's biggest copper porphyry deposits.
So this has implications for the type and scale of mineralisation that one day might be found along the Stavely Arc. Back in Melbourne, I asked David to sketch the two sides of an Andean-type subduction system.
On one side there's continental crust, which is quite light, and on the other side there's thinner but much denser oceanic crust. And the oceanic crust, when it pushes up against the continent, because it's denser, it'll sink down underneath. We call that subduction. And as it goes down, it induces melting in the mantle way deeper than the crust. And those melts will come towards the surface as hot magma through the edge of the continent, close to the ocean, and make a set of volcanic eruptions. And in the process of that happening, the rocks that were out in the ocean, where it was cold, they get metamorphosed, changed into rocks which are quite cold. But above the continent, where there was the hot magma, it's quite hot. And so there's this change in metamorphic grade and temperature we call a paired metamorphic belt. And as the direction of temperature changes from cold to hot, it tells you which way the subduction zone must have been dipping in ancient times, even though we can no longer see it.
Paired metamorphic complexes are really key things to recognise in an ancient rock record. They tell you that you're on a convergent boundary. They tell you that you'd expect to have an intervening magmatic arc. They also tell you the subduction zone polarity.
So how do we know that?
By comparison with modern day subduction accretion systems.
Paired metamorphic complexes are found to straddle modern-day subduction zones from South America to Japan. The significance for Stavely was recognised by a University of Melbourne team headed by John Miller and Chris Wilson. They realised that the hot metamorphic rocks west of Stavely and the cooler metamorphic rocks to the east were the same age. and must represent an ancient example of a paired metamorphic complex. After seeing the cooler but high-pressure rocks near Ararat, we decided to have a closer look at the high-temperature but low-pressure belt in the Glenelg zone.
So what's the significance of this outcrop?
Well, the Glenelg metamorphic complex here is exactly the same age as the metamorphic rocks east of the Stavely Arc, but these rocks got so hot that they actually started to melt. So what we have is evidence that the Stavely Arc has high heat flow on the western side to form these partially melted rocks versus low heat flow on the eastern side of the arc. This is where the concept of paired metamorphic complexes comes from. It's really crucial information because it tells us at the time the Stavely Arc was forming, the subduction zone was dipping west beneath Gondwana and the arc was being built along the eastern edge of Gondwana.
The evidence was stacking up. The Stavely volcanic rocks were part of a magmatic arc. But if so, they should form a huge mass in the deep crust. The team needed to bring a technology to the project that would test this.
So after the work had been done that established we had a likely paired metamorphic complex and arc system in Western Victoria, and we thought it was time to really test this. And the best way of testing it in an area with poor outcrop was using deep seismic reflection.
This extraordinary technology would give the team's geophysical experts a picture of the Earth's deep structure across Stavely.
So we had trucks go along in Western Victoria and collect very deep, up to 60 kilometre depth seismic, and it completely changed our understanding of how Western Victoria fits together in terms of its crustal architecture.
Like an ultrasound, but on a huge scale, a seismic survey creates an image of the Earth. With this image, a geophysicist can delineate the major rock layers that lie directly beneath the survey line.
And what that gives us is a cross-section of the crust, so we can see the geometries of these belts and of the rocks with depth.
Back in 2006, the first survey led to a huge advance in the knowledge of Victoria's geology and gold prospectivity across 3 of the state's geological zones. So in 2009, the Geological Survey headed to the Grampian-Stavely zone. This time, the trucks would cross the Stavely Arc.
What we could see in that data is a big reflective body occupying the mid and lower crust of the Grampian-Stavely zone, and that's precisely where we've got these sort of Stavely andesitic rocks exposed at surface. We think that is the magmatic arc. It's just hidden mostly underneath younger sediments.
The field mapping, the geochemistry and the paired metamorphic complex were all evidence of the buried magmatic arc. Now the seismic images had revealed its true depth. The Stavely Arc was big, just what you would expect with a buried arc. Now the team could confidently visualise the ancient landscape.
Well, 510 million years ago, this was a really interesting part of the world. We're right on the eastern edge of the Gondwana supercontinent. To the west lay the supercontinent of Gondwana, landmass for thousands of kilometres, and the Pacific Ocean, the Paleo-Pacific Ocean, would have extended for thousands of kilometres to the east. The rest of Victoria did not exist as a landmass at that time.
So back then, what would this margin have looked like?
So the Stavely Arc 510 million years ago was an active arc. There was arc volcanoes lined up all the way along the eastern margin of Gondwana, facing the Pacific Ocean. It would have looked a little bit like the Andes.
So the team's work was pointing towards an Andean volcanic arc, active 500 million years ago and buried in the Grampian-Stavely zone. But if it's like the Andes, it has to be big. So where does it go? And how big is it? The seismic revealed its depth, but in one place only. The team needed a way of looking through the younger cover rocks, but they can range from 10 to 300 metres thick. It would take a dedicated technical team in Melbourne and a holistic approach to solve this problem. This is where all the data is collated, the maps are prepared, interpretations are tested, and projects are planned. And the geophysical experts can use new high-tech data to visualise, deeply buried features.
Geologists from not too many generations ago would be quite astounded about some of the features that we can see and some of the questions we can potentially resolve from using geophysics, but only when we're integrating those with robust geological field observations.
Definitely the main data sets that we found useful was the gravity and the magnetics. So with those data sets, we're able to strip away some of the younger rocks that aren't really of interest to us, and they enable us to look deeper at the older rocks that we're really interested in.
Magnetic data is typically collected from aircraft flying in a preset pattern. Gravity is mostly collected on the ground by recording the density of the Earth's crust at thousands of separate stations.
How deep can you see here?
So the magnetics looks down to about 30 kilometres. With gravity we can see a bit deeper.
Looking this deep would have been a wild dream for the 19th century geologists. But it all became possible in the 1990s once the whole state was surveyed by the Geological Survey. And Victoria has some of the highest quality magnetic and gravity data available. Senior geophysicist Suzanne Hayden describes the extent of the gravity data.
The whole state is covered at about 1.5 kilometre station spacing, which we would call a sort of regional to semi-regional coverage. And we did some gravity traverses across the project area. So we did, I think, 16 odd traverses at 200 metre station spacing.
Now with the tools to look below the younger cover rocks, Phil could finally trace the Stavely Arc's true extent.
So what we can see here is all these yellow regions is that cover that I was talking about. And what we can do with the magnetics and the gravity is basically strip that away, so we see all these features from the deeper, older rocks that we're really interested in. So you can see here the amount of detail that we get when we lift that cover and when we're looking at the deeper, older rocks.
Now they could see the true extent of the Stavely Arc rocks. The geophysics revealed 19 belts of volcanic and intrusive rocks. All these rocks were formed in the original magmatic arc during the Cambrian. But now they're mostly buried by the younger basins. So by combining this new horizontal map with the vertical data from the seismic survey, it was possible to visualise the present-day Stavely area in 3D.
Part of the problem with geology is understanding geometries or shapes of geological structures. So we need a 3D room to be able to visualise those geometries.
The team needed to bring together the mapping and the geophysical data, and 3D visualisation was the obvious choice. Dr. Mark McLean is a specialist in this field.
So when something works in map view, doesn't necessarily mean that it works in 3 dimensions. And that happened a lot. We would come across problems in 3D and then we'd have to go back and revisit the structural interpretation to be able to create something that was actually possible in 3 dimensions.
We can use the magnetics and the gravity to plot a whole bunch of transects throughout the area that we're looking at, and using the seismic we can extrapolate from that region of control using the other data sets to give us a whole series of cross sections that we can then use to help build our 3D model.
When we brought the seismic data into the 3D model, it really brought up some changes in our understanding of the crustal architecture in Western Victoria. It changed what we think about some of the geometries of those different faults and what we think the shape of those Cambrian volcanic belts actually is. And we think that this was a pivot point that led to a change in understanding for Western Victoria in terms of copper discovery.
The modelling showed great complexity in the Stavely Arc. This was partly explained by an event at 500 million years ago, which had both shut down the arc and then faulted and tilted all the rocks. But it seemed to the team that something else was at play.
We had some very curious and hard to understand structures in the Stavely Arc, and it was really causing us problems in trying to interpret how the different Cambrian arc belts, the fault slices, fitted together and might correlate with one another.
Needing to understand this complex jigsaw puzzle, they realised the complexity would make sense if the Stavely Arc had been deformed more than once. and they found the evidence in the Grampians.
I think the really eureka moment was getting some understanding that the structures we mapped in the Grampians could be traced into the underlying Cambrian bedrock. So now we had the opportunity to use the structures we could see in 3 dimensions in the Grampians and apply them to the underlying bedrock where the outcrop's really poor.
So the Grampians was the key to unlocking the Younger deformation. And now they could put more dates on the geological timeline. At about 440 million years, the deep ocean retreated eastwards, and the Grampian strata were laid down on top of the Stavely Arc. Then, at about 405 million years, the Grampians had its first taste of tilting and folding. But this movement also affected the older Stavely rocks. Once the team understood this, it was possible to unwind this Younger deformation.
Using the geophysics and using the other data sets that were available to us, we've been able to retro-deform or undo that deformation and visualise these rocks as they would have been in the Cambrian.
Now they could run the timeline backwards to see what the arc looked like at 500 million years.
Now we understand the deformation history of the Grampians, we can use that as a template to show how those 19 belts really originated as 3 or 4 continuous belts, fault slices of Stavely Arc volcanics.
This is a good example of why the Geological Survey maps all rocks, irrespective of their potential resources. They need to understand how the landscape evolved as an interactive system. So while the Grampians rocks themselves are not prospective for minerals, they provided the key to how the Stavely rocks had been pulled apart.
So it actually took a really holistic, whole of systems approach to draw all these diverse strings together to come to a story that everything seemed to sing off the same song sheet. It was a fantastic breakthrough. It's one of the reasons you do geology, because it's just fun when it all starts to work.
So now the Geological Survey had a solid theory, backed up by the geophysics and their years of mapping. And the shapes in the Grampians told them about the Arc's final structural history. Other members of the team can now better understand Stavely's mineralisation. Melanie Phillips and her colleagues compiled all the data from 50 years of private mineral exploration.
The Geological Survey has gone back through over 1,800 reports, company reports that were submitted in and around the Stavely project area. We found there was over 30,000 surface geochemistry samples within those reports and almost 10,000 drill holes.
But most of this work by private companies was done on or near exposed rocks, and the buried basement had hardly been explored.
So that left a massive amount of the Stavely project area that hadn't even really been tested. And a lot of the drilling didn't actually penetrate deep enough to get an adequate sample of the basement rocks.
This highlights why government geoscience research is needed to assemble all the available data. While private companies usually focus on small areas, the Geological Survey can look at the big picture. And this applied research is shared at conferences like this one. It inspires collaboration and new directions for investigation. Dr. Rob Duncan is part of the Geological Survey team and one of the scientists who evaluated the mineral prospectivity of the Stavely system.
So can you explain to me the main types of mineralisation that you might find at Stavely?
We're talking about porphyry, epithermal and volcanic hosted massive sulphide mineral systems.
If we could go back to the Cambrian and see one of these VHMS deposits forming, what would we see?
So they'd be pretty similar to black smoker environments that you see today. So there'd be acidic fluids upwelling through the oceanic crust. You'd see accumulations of metal forming chimneys on the seafloor.
Volcanic hosted massive sulphide deposits, known as VHMS, form directly on the seafloor where ocean crust is stretching and away from the subduction zone.
So sitting in the forearc or in mid-ocean ridge basalt that sit more in the back arc.
In contrast, the porphyry and epithermal mineralisation forms below the surface and is related to products of the subduction zone.
So a porphyry system is related to a igneous intrusion that happens at quite a significant depth beneath a volcano. And porphyries and epithermals are both linked, so an epithermal would form closer to the surface, closer to the actual surface expression of the volcano.
So what evidence do we have that these deposits will occur at Stavely?
So in the very limited area of outcrop that we have at Stavely, which is 3.5% of the 20,000 square kilometre project area, what we see in those are significant mineral occurrences that have all the trademarks of these mineral systems that we're talking about. So there's actual mineralisation, there's veining, there's hydrothermal alteration.
To find when mineralisation occurred, we have to go back along the timeline to around 500 million years ago. This was late in the Arc's history, just as it was shutting down.
It goes out with a bang. It goes out with a last pulse of metalliferous porphyry deposits and granites that intrude into the upturned fault slices of the Arc. It's gone from a change from the Arc being shortened and squashed to suddenly being released into extension again. And in metal systems analysis, this is actually quite a good scenario for the mineral prospectivity of the Stavely Arc. A final release of this confining pressure has resulted in a pulse of magmatism, and that's brought these metalliferous granites and porphyries towards the surface.
The Geological Survey could now understand how the Stavely Arc had formed and the types of mineralisation, but they still needed to raise samples of Stavely's buried rocks from below the plains to confirm their presence, check their geochemistry, and to better constrain the timeline. There was only one way to achieve this.
We were at a point where drilling was the only way forward to understand more about the older rocks undercover. We're a relatively small team at present, and we needed to seek out collaborative opportunities to bring the niche skills and knowledge and expertise to get the very most out of this project. And Geoscience Australia were a very favourable partner in that, in being able to deliver some of these skills such as geochemistry and geochronology.
The reason we were attracted particularly to Stavely and why it was the first cab off the rank, decades of previous work, particularly the big seismic work, the chemistry work, the mapping work, and there was a new tectonic model that was being developed by the Geological Survey of Victoria, Ross Cayley, and that was something that we could go and test, and so we decided to partner with GSV back in 2013 and start the project, and now we're seeing today the fruits of that labour.
The new partnership completed 14 stratigraphic drill holes, so now they had samples of the volcanic and intrusive rocks that could be geochemically analysed, as Geoscience Australia's Anthony Schofield explains.
So basically what we found is that wherever we got volcanic rocks, so andesites and dacites and things like that, and related intrusives, that they were part of the Stavely Arc package. They had a clear subduction signature, they're part of a magmatic arc setting, which is the right kind of environment for forming large copper gold deposits. We also saw that a number of the arc rocks have very similar compositions to what we know from the Mount Stavely volcanic complex, which we know has a lot of mineral potential associated with it, so we can extend that mineral prospectivity all across the Stavely Arc with a degree of confidence.
The drilling also had another benefit. Dr. Rob Duncan showed me how it helped to demonstrate that mineralisation can occur in a variety of rocks, both in and outside the volcanic belts.
So what we've got here, Clive, is an example of potassic alteration, so K-feldspar and magnetite, which are typically higher temperature and more likely associated with a productive mineralised system. In addition, it occurs in the sedimentary host rock and not in the volcanic rock or the igneous intrusion itself. So through the work that we've completed, we actually think mineralisation can form in a lot of those Cambrian rocks. So it doesn't necessarily need to be hosted in the volcanic belts themselves, and that's a significant finding because it greatly increases the mineral exploration search space throughout the region. So they can occur in sedimentary rocks that occur between the volcanic belts, as long as they existed at the time of these magmatic systems that we're talking about.
The final aim of the drilling was all about time and checking the early history of the Arc by measuring the age of the rocks.
And it's possible to do that because some of these rocks have got tiny mineral grains in them with radioactive elements that allow us to date the actual age of the formation of that rock. And that's a really critical part of the story.
It's new data. No one else has dated that zircon before. And you're the first person to do it, and you can be the first person to put an age on a rock. That's really exciting. That's so much fun.
Geoscience Australia's Chris Lewis was the team's geochronologist. It was his job to find the age of the rocks by analysing the tiny zircon crystals and to find out how long the arc had been active.
And what was interesting, that the geochronology that came out of this hole, it was slightly older. It was about 510, 511 million years old. Whereas further to the east in the Stavely belt, it's more around 500, 503 million years old.
The team could now fill in the early part of the timeline. From 511 to 500 million years ago, the arc had been active based on the zircon age data. But other data suggests the arc began even earlier, around 522 million years ago. So for over 20 million years, the Pacific tectonic plate had subducted beneath Gondwana's margin. The massive heap triggered volcanic activity, seafloor mineralisation and metamorphism, followed by intrusions of granite. Then, at 500 million years, the Stavely Arc shut down, and at the same time, it was cut into the 4 separate belts of volcanic and intrusive rocks. But then, at 405 million years, these 4 belts were twisted and rotated, along with the Grampians.
So a previously simpler Cambrian system, including the porphyries, was suddenly reconfigured and torn apart and locally rotated and offset along these younger structures, and the Grampians is the key to understanding that part of the story.
Over a period of about 100 million years, the Stavely Arc was formed, became extinct, and then was ripped apart. But from 400 million years ago, it was all over, and that in itself reveals something extraordinary about the landscape.
It's absolutely amazing how stable this part of the world has been since that time. It's the reason why the upper levels of the Stavely Arc are still preserved. They're the most economically interesting parts. Most old systems, you'd expect them to be eroded away. The special set of circumstances we've got in Western Victoria has seen these 500 million year old upper crustal levels preserved to the present day. And that makes this a really interesting terrain from an exploration point of view.
It's always been the job of the Geological Survey of Victoria and Geoscience Australia to share their discoveries with industry and other researchers, and more importantly, with those who pay for it, the Victorian and Australian people. So through their publications and conferences, new data and knowledge is freely available. It's amazing how far we've come in 150 years in our understanding of Earth's history, our use of modern technology, and now our ability to share all this information with everyone worldwide.
Ferdinand Krauser and Norman Taylor would have been blown away by the latest technology and our new understanding of the dynamic Earth and of plate tectonics.
The Geological Survey of Victoria and Geoscience Australia looked at every aspect of the Stavely Arc, its rocks, its structure, its geochemistry and the age. This group of people put all that information together to achieve a holistic view of Earth dynamics that we can share with the Victorian community and geoscientists around the world.
Each generation uses the ideas and technology that it has available. But what links geologists across all generations is this desire to understand the planet we live on.